Hey, it's Ryan. This is a brief lecture on another phenomenon of light known as polarization. Polarization, if you recall from one of our videos, is the removal or realignment of components of a light wave. And it basically matches a transmission axis of a polarizing lens, or the polarization matches the reflection, the oscillations of the particles that are reflecting it. But I'll show you this. So anyway, in general, polarization is the removal or realignment of components of an electromagnetic wave. And so the way that we often will show this is really through two ways. There's polarization through polarizing lenses. A polarizing lens will have a transmission axis, and the easiest way to show this would be diagrammatically. Many of you probably have sunglasses that are polarizing. Diagrammatically, what we usually will do is have some sort of transmission axis here, and on that axis we'll have unpolarized light. And so the way we usually do that is with a combination of all the directions. So our incoming light is oscillating in any and all directions. This is unpolarized light. And we would say that this unpolarized light has some initial intensity, S sub O. And that light will propagate along the transmission axis until it's incident on a polarizing lens. So what I would like to try to do is copy this out a little bit. And this works well enough. So we have our light propagating along the axis like so. We could even show that. V, which is the speed of light. And in our case, it'd be in the x direction. And that light will be incident on what we will call a polarizing lens. And so that polarizing lens will have some thickness and a transmission axis like so. And so what it will do, a lot of times I like to think of polarizing lenses kind of like picket fences. So the slats, the openings in the picket fence will allow the oscillations of the light through, and the slats that aren't holes will block any oscillations in any other direction. So the point is we will get out of this just linearly polarized light in the same direction as in the same direction as darn, it's just not working. Anyway, it'll keep going in the same direction as the transmission axis. And so we have all this polarized light. This is polarized. And this, we might note, is our transmission axis. And our transmission axis gives us the direction of the polarized light. So this is polarized light, and that polarized light will have an intensity S1. And S1 will be half of the initial intensity. It's only letting half of the oscillations through, no horizontal, only vertical. And so what we often would do is this would continue on. So imagine that we're just continuing this on. So this is all the same transmission axis. So we have our continuation of the same transmission axis. Now we have just our linearly polarized light traveling along S1, and this will be incident on another polarizing lens. And so we'll draw another polarizing lens. And that polarizing lens will have a transmission axis like so. And so now you can see, try to do this in a different color. That was our initial transmission axis. And so there's an angle theta between the initial transmission axis of our first lens. So we'll call this the transmission axis 1. And this is our second transmission axis now, the blue one. And that's going to emit light only oscillating in the same direction as its transmission axis. And so that will lower the intensity of light as well. So this will be S2. And S2, we use something called Malice's law. Malice's law, which states that S2 will equal S1 times the square of the cosine of the angle between the transmission axes. And so this is how we'll work with any polarization problem. We should also discuss this idea of intensity of light, because I've talked about it a few times. In general, emitted light, we rate how much light is being emitted with something called the intensity. And intensity, if you can imagine a light bulb, so maybe we'll look at the diagrammatic. We might have some sort of light bulb, like so. And that light bulb might be giving off light. And now the way that we can think of this is that it's giving off these spherical waves of light in every direction. And so you can imagine that as we go farther and farther away, that might be R1, that might be R2, and that might be R3. The amount of light is getting spread out over the distance, and so the intensity of light that we would see if we were looking at this light bulb from here would be greater than if we were looking at the light bulb from here, right? And you can kind of imagine that. If you get really close to a light bulb, it feels more painful than if you're farther away from it. That's just because of the intensity of light. And so in general, intensity is just basically the power over the area that it's distributed. And so we can show you this mathematically as well. So anyway, it's the power over the area. So we'll show you mathematically. Mathematically, we have S intensity is equal to the power, the wattage, if you will, over the area that it's being distributed. And so we'll define S as intensity, P as power, usually measured in watts, and A is the surface area for which the power or the energy is spread out. Surface area of the wave front. And so there it is. So intensity of light, which you're more used to than you would have thought, lowers with distance, but it also can be lowered with polarization of light. And we use Malice's law if we use multiple polarizers. Otherwise, we know that the polarizers are cutting out half of the light. And if you've ever worn polarizing sunglasses, you may have noticed that. All right. Thank you.